So design of combined footing. So first question, design a combined rectangular footing for two columns A and B carrying loads of 500 kilonewton and 700 kilonewton. Column A is 300 mm by 300 mm in size and column B is 400 mm by 400 mm in size. The center to center spacing of column is 3.4 meter. The safe bearing capacity of soil is 150 kilonewton per meter square. Use M20 concrete and Fe 415 steel. So what is combined footing? Combined footing means the footing which support two columns. So here one column is column A and next one is column B. So first column carrying load 500 kilonewton, second column 700 kilonewton, and size of the first column is given as this one and size of second column is this. Then the spacing between, that is center to center spacing of the column is 3.4 meter. Then the safe bearing capacity of soil is also given. Okay, so the maximum bearing capacity, that is the soil can bear only 150 kilonewton per meter square. So we can design the footing column support column supporting footing with the load below 150 kilonewton per meter square. Then M20 and Fe 415. FCK 20 Newton per mm square and Fy is 415 Newton per mm square. So please by heart the question, okay, because all the question is the procedure is same. So first, if the data are not given, please assume the data. So, okay, so first write the given data. Okay, first write the given data. First step is calculation of total service load. So first load on A is given as P1, load on B is given as P2, total load is P1 plus P2. Then thus we want to calculate self weight of footing, that is PO, that is 10% of that load, that is 10% of total load. Okay, 10% of total load. So 10 divided by 100 into this value. Then total service load means the total load plus the self weight of footing. Okay, total load plus the footing has its own self weight gives the total service load. Then calculation of area. So after calculating total service load, we want to calculate the area of footing. How to calculate? Area equal to load divided by bearing capacity, that is what area equal to load divided by bearing capacity. You know that load equal what stress equal to load by area, that is here the stress is load bearing capacity. So from that area equal to load divided by safe bearing capacity. So load we want to take the total service load divided by bearing capacity given in question is 150. So we get 8.8 meters square. So we want to assume the length of footing. So how to assume length of footing? We know that the center to center distance the center to center distance, assume this is column A, this is column 2, then the size of column A is 300, column B is 400, center to center is 3.4 meter. Okay, so center to center distance is 3.4 meter. So 3.4 meter plus the remaining portion, that is the half of the column, that is 0.15 and 0.2. So that gives 3.75 round 4. So we want to give also the end distance, that is we want to increase the total distance from the one column to next column by increasing some value. The distance from one column to the column A to column D, this is 4. So increase the or assume the length which is greater than 4. So we take the length as 5 meter. Okay, center to center distance 3.4 meter ഉണ്ട്. നമുക്ക് ഒരു കോളത്തിൽ നിന്ന് മറ്റേ കോളം വരെയുള്ള ഡിസ്റ്റൻസ് ആഡ് ചെയ്യണം അല്ലേ. ആഡ് ചെയ്യണം, എങ്ങനെ ആഡ് ചെയ്യും? നമുക്ക് കോളത്തിന്റെ value for the size of one column is 300 mm, 400 mm. So 3.4 plus half of this and half of this gives the distance between this one to this one, and we want to provide the end distance by increasing that total value. We get 4, then we provide, assume the length of the footing which is greater than that value as 5 meter. So again we want to calculate the width by, we know that area equal to length into breadth. So width equal to area divided by length, that gives 1 width. So again we want to calculate the area provided because the area is changed. So length into that, because the width is rounded. So we want to calculate the area provided by multiplying with length into breadth, that gives 9 meters square. Okay. Area provided equal to length into breadth equal to 5 into 1.8 equal to 9 meters square. Then we want to calculate the center of gravity of loads. Okay, the center of gravity of loads, we have an equation that x bar equal to P1 x1 plus P2 x2 divided by P1 plus P2. So what is x bar? The distance of center of gravity of column loads from the center of column S. So x bar is the center of gravity of due to this column loads, which is from the distance of the this x bar is the distance from column A. So x bar equation, so x1 is distance of P1 from A. X bar means, x1 means the distance of P1 from A. So distance of P1 means 500 from A is not. So the x1 equal to 0. Then x2 is the distance of P2 from A. Distance of P2 from A, that is 3.4 meters. So we want to provide the value. So 500 into 0 plus 700 into 3.4 divided by total loads 1200. This 1200 is the total load, not service load. It is the total load. So okay. And then we get 1.98, we rounded as 2 meters. So x bar is the distance, that is center of gravity distance from the center of column. So we marked a center of gravity line and we get the value from the center of A as 2 meters. So we are going to assume this center of gravity acting at equally on the column. That is, if we know that total length is 5 meter, the half is 2.5 meter, 2.5 meter. So the center of gravity is acting at the center portion, and x bar is the center of gravity from the column A. Okay. We know that the size of the column is 300 mm. So this is 2 meter. So the remaining is 0.15 meter. That is 300 mm. So here it is 0.15 meter. So 2 plus 0.15 meter. That is 2.15 meter. Then 2.15 meter. Then subtract 2.5 minus 2.15 meter gives the end distance as 0.35 meter. So similarly you want to calculate this distance also. Okay. Then calculate step 3, calculation of net upward pressure. So net upward pressure is load by area. Load is the total load divided by area is 5 into 1.8. So that gives 133.33 kilonewton per meter square. Okay. Then pressure, we want to calculate pressure per meter length, that is multiplying it with the width value, which gives this 240 kilonewton per meter. So pressure per meter length is the value 240 kilonewton per meter. So next step is calculation of shear force. So calculation of shear force, the procedure is we want to by heart, okay. So we have four steps. One is we want to calculate shear force to left of A, then shear force to right of A, then shear force to right of B, and shear force to left of B. So this procedure you want to by heart. So first shear force to left of A. So we want to consider shear force to left of A. That is the shear force to left of A is the column A is this one. Okay, left of A the only the pressure acting upwards. So take that pressure. Okay, 240. How much distance is this? This is 0.5 meter. Okay, 0.5 meter. We know that the edge distance is 0.35 meter and this is 0.15 meter, that is 300. Okay, the center of this 300 to this one, that is 0.15 meter. Add this value which gives 0.5 meter. So 240. That is a UDL value. So 240 into 0.5 meter gives shear force to left of A. Next one is shear force to right of A. Shear force to right of A means just includes this value with 500. That is 500 plus 120. But this 500 is acting downward. So assume this downward force of the left side of the column as negative. Okay, that gives shear force to right of. Then shear force to right of B. Shear force to right of B means B is this, right of B only consider this UDL value. So in the right side the upward force is taken as negative. Okay, then negative this into this this edge distance, that is 1.1. Okay, 1.1. Then shear force to left of B. Shear force to left of B means just include that UDL with this 700. Then the downward force on the right column is positive. So add this value with this 700 gives shear force to left of B. How we get that 1 meter value? That is, we know the center to center distance is 3.4. So this 3.4 minus 2 meter gives the remaining portion of this to this. Okay, then we know that the distance of this column as 400. So take the half value, that is 3.4 minus 2 gives 1.2 meter, plus this 0.2 meter gives the center to center distance with this one. Then subtract this 2.5 with that one. Okay, that gives 1.1 meter. Okay, then we want to know the distance where shear force will be 0. So this shear force will be 0 distance is where the maximum bending moment acting. So shear force will be 0 at x distance from extreme left. So we want to calculate this x distance. How to calculate? 240, that is the upward pressure into this distance. That is 240 is acting into this distance, that is x, minus this 500 equal to 0. Because this is UDL value, convert it into normal load, minus this 500 gives the shear force, shear force up to this center of gravity or the x bar distance. Okay, so we want to calculate the shear force will be 0 at x from extreme ends. So 240 into this what x distance and the 500 up to 500. So these two values are the shear force within the x distance. So from that equation we want to calculate x. So 240 into x gives the shear force from this extreme to this x distance. Then 500 equal to 0 gives the distance of x. Okay. Then we want to calculate the calculation of bending moment. So bending moment, first you want to draw the figure. Then we calculated this x distance as 2.08 meter. Okay, 2.08 meters. So we take that 240 into 2.08. So we calculated this 2.08 to calculate the moment. Okay, so 240 into 2.08. That gives the UDL. So how to calculate moment? Into 2.08 divided by 2 minus 500 into this distance, that is 1.58. Okay, so please calculate this 1.58 by drawing this figure. Okay, how to calculate 1.58? That is what we know that the shear force is 0 is from 2.08 to 2.08 from this point. Okay, so ഇങ്ങറ്റം തൊട്ട് ഇവിടം വരെ എത്തുമ്പോഴാണ് എന്ത് ചെയ്യുന്നത്, അതായത് 2.08 എത്തുമ്പോഴാണ് ഷിയർ ഫോഴ്സ് 0 ആവുന്നത്. സോ വി വോണ്ട് ടു കാൽക്കുലേറ്റ് ദ റിമൈനിങ് വാല്യൂ, ദാറ്റ് ഈസ് 500 എവിടെയാണ് ആക്ട് ചെയ്യുന്നത്, ഇവിടെ. അപ്പോൾ ഈ 500 തൊട്ട് ഇത്ര ഒരു ഡിസ്റ്റൻസ് കണ്ടുപിടിക്കണം. അപ്പം നമുക്ക് എന്ത് ചെയ്യണം, 3.4 ആക്ട് ചെയ്യുന്നതുണ്ട്, അതിൻ്റെ ഹാഫ് പ്ലസ് 0.8 എടുക്കണം. അതിൽ ആൻഡ് മൈനസ് ദാറ്റ് വാല്യൂ minus 2.08 with 0.5 meter gives what, 1.58. Okay, so this to this 2.08 minus 0.5 gives the 1.58. Then you want to calculate the equation. Okay, you want to calculate the equation. Then sagging bending moment at B and sagging bending moment at A, that is where the load acting, that where the sagging happens. Okay, load act ചെയ്യുന്നിടത്ത് sagging ഉണ്ടാവും. So the load acting portion undergoes sagging. Okay, the load acting portion undergoes sagging. So how to calculate sagging bending moment? Sagging bending moment means what? Calculated it using the pressure, that is 240 into calculate 240 into 1.1 into 1.1 into 2. So 1 point, how we get 1.1 from this figure. Okay, from this figure we get 1.1, that is the center to this point. Okay, center to the extreme point, center of the B to extreme point gives 1.1. Same that the sagging bending moment at 240 into 0.5 into 0.5 divided by 2, that is the center of this column to the extreme end gives the sagging bending moment at A. Then we want to calculate sagging bending moment at outer face of column B. So 240 into assume the outer face distance, that is the end of the column B to the extreme end distance is 0.9 meter. So 240 into 0.9 square divided by 2, that is 0.9 into that equation. Okay, that gives 97 kilonewton meter. So first we want to convert this 240 UDL value into normal force into that. How to calculate moment? By taking the half of the distance. Okay, so every column has the same procedure. Then sagging bending moment at outer face of A. Then point of contraflexion. So point of contraflexion is the distance point of contraflexure occurs at distance x from the center of column A. So we want to calculate point of contraflexure. Okay. So the moment we want to calculate about the distance this point of contraflexure acting. So the moment at the moment at x distance, how to calculate? Assume from this column to x distance the point of contraflexure acting. So we want to assume the downward portion load is acting as minus. Okay, we want to calculate the moment. So assume this the from this column to x distance the point of contraflexure acting. Assume the anti-clockwise moment as negative so assume this point as the point of contraflexure. So we don't know what is the distance from this column, so assume this as x. Then 500 into x minus 500 into x, then 240 UDL is or pressure is acting from the soil towards this footing, that is 240. So assume this distance, take this distance as 0.5 meter and x. So 240 into x plus 0.5 into x plus 0.5 divided by 2. So that gives x value. So take the x value. Okay. So we get two values x1 and x2. So take the less value and so here we get 0.81 and 0.81 and the next value is taken from this column B to this point. Okay. 0. So similarly, we want to calculate the point of contraflexure from B by that equation. Then we want to calculate shear force at first point of contraflexure and second point of contraflexure. So we want to calculate the shear force at first point of contraflexure and second point of contraflexure by this equation. So this minus 380 we already calculated in shear force to right of A, that is inside column shear force of right of A and left of B, that is inside column B. So we want to take these two values. Okay. So first point of contraflexure is near to A. So first we want to take that minus 380 plus 240, that is the upward pressure into 0.81 and shear force second value is the this point of contraflexure near to B, that 436 is taken from the shear force to left of B, that is inside of B 436 into same that, but the sign is different. Okay. Then you want to draw the shear force diagram and bending moment diagram by calculating all the values. Okay. Okay. Then step 6, calculation of effective depth mu equal to mu limit. So we get a moment we get a moment, that is this 271 kilonewton meter. Okay, 271 kilonewton meter. Provide that into mu by multiplying with 1.5 and we know the equation 0.138 FCK BD square. So calculation of effective depth by using this equation. Then after that we want to calculate the effective effective depth check for punching shear. Okay, so we are going to take the critical plane line. Critical plane is around the column 2 at the distance d by 2. So we know the d by 2 distance is d is 300 mm. So d by 2 is 150 mm. So along this 150 mm the critical plane, that is the maximum shear force or punching shear acting due to punching shear, the column column B, around column B, we taking it as critical plane. Okay. Then you want to calculate VU2 by using this equation and B0 by using this equation. D by 2 plus D by 2 plus the size of the column gives the B0. Okay, critical plane equation. And tau V, you want to calculate nominal shear stress, tau V. So the tau V, you have an equation, so provide all the values and we get the tau V. Then nominal shear stress tau V, then permissible shear stress tau C into K, assume K as 1. Then you want to check this, but this check is here the tau V is greater than tau C into K. So tau C is critical or permissible. So tau V is greater. So the footing is not safe. Footing not safe. So increase the depth by using again this equation by providing replacing tau V with tau C into K, and from that equation we get the D value. Okay, we get the D value. Then assume the effective cover 60 mm and overall depth as this one. Then calculating the calculation of reinforcement by using this equation. Okay, calculating the reinforcement by using this equation. Just provide all the values and calculate the number of bars. Then the reinforcement for sagging bending moment you want to calculate. Okay, you want by taking the moment as 97, sagging bending moment as 97. Okay, the sagging bending moment at the outer face of B is 97, so take that value, and mu2 is, and again you want to provide this equation for AST2, then D, and then number of bars. Okay.